This is Physics 30, Chapter 5, Lesson 3 on collisions. When we talk about collisions, we have two primary types that we'll deal with. We have perfectly elastic collisions and perfectly inelastic collisions. So the distinguishing features between the two. In perfectly elastic collisions, we have scenarios where the objects bounce off of each other. We have that the total momentum is conserved. Momentum before the collision is equal to momentum after the collision. And the same thing for kinetic energy. Total kinetic energy before the collision is equal to total kinetic energy after the collision. Now, if we think of any kind of collisions, one typical example is something like a car crash. When something like that happens, you're going to lose a lot of kinetic energy from your system into things like friction, heat transfer, all of those kinds of things. So there's really no scenarios where you can actually perfectly conserve all of that kinetic energy within the system. And so real-world examples for perfectly elastic collisions only actually exist at the atomic level. We can find certain examples between gas atoms colliding and perfectly conserving their energy, but for the most part, they don't really exist in the real world. So the reason we still use them or discuss them is because we can get very, very close approximations. In rigid systems, where collisions happen between things like pool balls when you're playing pool, or between the balls of a Newton's cradle, those are very, very close to perfectly elastic. So we're happy enough to use the equations and approximate that they're close enough. But just so that you know, technically, true examples don't really exist aside from the atomic level. In perfectly inelastic collisions, the objects will stick together. Total momentum is still conserved. Momentum before equals momentum afterwards. However, total kinetic energy is not conserved. So for perfectly elastic collisions, momentum before is momentum afterwards. So we have this equation. We know that momentum will be mass times velocity. So we have the initial mass and velocity of object 1, adding to that the initial mass and velocity of object 2 will be equal to the mass and velocity of object 1 with the final velocity and the mass and final velocity of object 2. For kinetic energy, we know that the kinetic energy formula is 1/2 mv squared. So again, we have the formula and equation using the mass and velocity of item 1 initially and item 2 initially. And then on the right-hand side, we have the mass and velocity, final velocity of item 1 and item 2. We also can get this helpful equation. Initial velocity 1 plus final velocity 1 will be equal to initial velocity 2 plus final velocity 2. Now, it's really important to note the differences in these three equations. Notice that with momentum and kinetic energy, on the left-hand side, you have both items 1 and 2, and on the right-hand side, you also have both items 1 and 2. Same thing for kinetic energy. However, with this final equation, notice that the left-hand side is both item 1 and the right-hand side is both item 2. So just bear that in mind when you're using these equations, that you're putting your objects or your items in the correct places. So take careful note of the subscript. With perfectly inelastic collisions, we still have that momentum is conserved, so we can still use this same equation. However, kinetic energy will not be conserved, so we don't arrive at either of the other two equations. We're going to look at some practice work on page 239, numbers 1 to 3, 6, and 8, as well as page 248, numbers 2 to 4.